Yes, huh? Alright, so before we start the class session, I would like to take the attendance from section 2. Siapa yang belum masuk within 30 minutes, we consider absent. Right, from the survey that I post yesterday or last 2 days, there's only like 7 to 8 people that can't join us today into this session. So I hope the other berapa kita ada 50 something. So the other 25 plus 25, 50, the other 40 can join the class as usual. Okay. Right. Section 2, group 1. We start. Amira Nur Sabrina. Kalau ada boleh cakap ya. Amira. Amshar, Iqbal.
Ada, madam.
Celia.
Ada, madam.
Chang Wei Li.
Yes, madam.
Dina Sofia.
Yes, madam.
Faris Akmal.
Yes, madam.
Ivan Yo Jin Siang.
Yes, madam.
Khairul Zamir. Absent. Mazlin Naziha. Daniel Haziq.
Yes, madam.
Oh, okay. I baru tanda tak ada orang. Right. Daniel Haziq ada. Syafiq Hakimi.
Yes, madam.
Now we are in week 9. Betul tak? 7, week 8 cuti. Week 9, alright. Amirul Iskandar.
Yes, madam.
Daniel Aiman. No. Akmal.
Yes, madam.
Aminul Mohazin.
Yes, madam.
Danish.
Yes, madam.
Ubaidullah. Sorry. No. Zuhilmi.
Yes, madam.
Ainul Hafiz.
Yes, madam.
Dah bangun ke? Korang ni atas katil ke di meja dah? Nur Izzati.
Yes, madam.
Nurul Nasa Huda. No, tidak. Siti Hajar. Ada.
Yes, madam.
Oh, ada Stakal Sanlaus.
Yes, madam.
Is it correct how I pronounce your name?
Yeah, correct.
Right. Tris Vita Kaul.
Yes, madam.
Yu Kyung Ji.
Yes, madam. Yes, madam.
Alright. AG Muhammad Nazmi.
Yes, madam.
AG stand for what? Awang.
Yes.
Okay. You're from Sarawak?
Sabah.
Sabahan. Okay. Takif.
Yes, madam.
Ada ya? Aiman Hakim. Name. Ang Wen Yok,
Yes, madam.
Akasha Daniel, okay. Arvin also tiada, masih raya ke Arvin ni? Badrul Munir, tiada. Gan Kai Ken,
Yes, madam.
Goh Chi Seng,
Yes, madam.
Grayson Gan Ka Seng, tiada. Hanis Hamizah,
Yes, madam.
Intan Sofia,
Yes, madam.
Irsyad, tiada. Khairatul Aisyah,
Yes, madam.
Imran Saharudin,
Yes, madam.
Zafran, Norman Hakim,
Yes, madam.
Atira,
Yes, madam.
Fatihah,
Yes, madam.
Firzana,
Yes, madam.
itu 7, 9, Nadira Natasha,
Yes, madam.
Arishah,
Yes, madam.
Safia, ada. Shah Hasrizal,
Yes, madam.
Sheikh Alif.
Yes, madam.
Alright, so let's see. Yang datang sekejap lagi boleh beritahu saya ya, nanti saya tanda attendance. Okay, so let's proceed to chapter 4 part 2, and for your information I have uploaded the lecture notes in the ULearn page, and then from now on every information regarding the lecture, please regarding this this course, you can refer to the ULearn. Okay, so if you have any question, you can just interrupt me during the session, and I think I can't go through the chat while the lecture session, because I afraid that it will I will miss all the information or all the question during the session. So kalau tak ada soalan, you all boleh mute dulu to make sure kita semua dengar dengan jelas. Siapa tu? Izzati, Anis, boleh mute dulu awak punya. Yes.
Saya Khairul Zami. Tadi time pun panggil nama saya tu wifi saya buat hal. So saya tak sempat jawab.
Okay. For the attendance, boleh cakap balik bila at the end of the class session. Nanti saya tanya balik. Okay, Khairul Zami.
Okay, bye.
Alright, thank you. Alright, let's start with chapter 4 part 2. Okay. So for this part, we will cover these 3 big chapter or big subchapter, which is a basic combination of logic circuit. How can we implement the combinational logic, and then the third one, how to use the NAND or NOR gate as the universal properties. Okay, for the basic combinational logic circuit, we will have 4 types of logic gates. First one is AND/OR gate. The second one is AND/OR inverter logic gates, and third one is exclusive OR, and fourth one is the exclusive NOR. Okay, for the AND OR invert, it's also known as AOI. So kalau you ternampak ada dia tulis AOI logic gate, it is referred to AND OR inverter logic gates. And then for the number 2, we have the how can we implement the combinational logic circuit. So the first one we want to to design or to build the logic circuit from the Boolean expression, and then the second one is how can we design the logic circuit from the truth table, and then the third one we have the NAND and NOR gate as a universal logic element, and then last one we will have the mixed logic. And I'm not sure whether we'll cover until I think for today we'll cover until NAND and mixed logic. For the NOR gate, if we have extra time, I will go through very fast about the NOR gate. Okay. Okay, let's see what is the AND OR logic. Okay, AND OR logic produce AND OR the SOP expression. So kita dah cover what is the sum of product terms in last session, where we have in general there are the AND and OR circuit, and it can have any numbers of AND gates with any numbers of input. So for this example, there are two AND gates with first one is AB term and the second one is CD term or CD input. So dua AND gates ni ada two inputs, AB and CD. This is the first AND gate, a second AND gate, and then they will combine by using the OR gate. Okay, so OR gate is to combine these two AND gates. All right, so we will get the X is equal to AB plus CD. Plus is the sum of the product. So the product is AB and CD, and we sum them together by using the OR gates. All right, and this is the example of how can we write the truth table from the logic gates. But I think I'm not sure whether, okay, so the output here is not really accurate, I think, but we'll try to go through one by one. So please remember that the SOP expression is always equal to 1 if at least one of the product term is equal to 1. So it means that kalau SOP, like I mentioned in the previous session, SOP we only refer to the output when the output is equal to 1. So there are 4 variables here. So 2 to the power of 4 is equal to 32. Betul tak? 2 to the power of 4, 16. 8 sudah, okay? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 16 So 2 to the power of 4 is equal to 16. And you need to write all the possible inputs for the A, B, C, D variables, and then write the output when you got the combination of A, B, and C, D. For example, this A, B, so you start from 0, 0, 0 until 0, 1, 1, 1, 1. So this is for first 8 variables, 8 possible input, and then the other 8 will be from 1, 0, 0, 0 until 1, 1, 1, 1. Okay, so kalau kat sini semua adalah kalau this is AND gate, so if AB is equal to 0 and CD is equal to 1, so we will get the output of AB 0 and CD is 1. So if any of these output from A, B or CD is 1, so the output will be 1. Okay, kalau you tengok kat sini mana-mana yang ada output sama dengan 1, dia akan keluar the final X ataupun final output will be 1. Okay, this is for the expression for SOP. So for the 0, the expression will be for the POS. Okay, so kalau kat sini A is 1, B is 0, so AB is 0. Okay, sebab dia adalah AND gate. And then if C and D both are 1, so the output for CD will be 1. Okay, so 0, 1 is equal to 1 and so on. So based on this logic circuit, you derive the expression by using the truth table. Okay. Okay, this is for AND OR gates. Let's see what is AND OR invert logic. Like I mentioned earlier, if you see the question or in the books, they write as AOI. It also refers to the AND OR invert logic gates. So we have the addition of inverter at the end of the output of the OR gate. So we have AB terms in the AND gates, CD also the combination from the AND gate, and then we will sum up terms 1 and terms 2 by using the OR gate. So we will have the A, B plus CD. So by adding the inverter, you will get the X is equal to AB plus CD bar. Okay, kalau ada inverter, so it means that you have the vertical line on top of the expression. Okay, so remember the De Morgan theorem, break the bar and then change the operation. So you have to break the bar, so you will get A bar plus B bar multiply with C bar plus D bar. So daripada SOP, we will get the POS expression. So what we can see here, or the conclusion that we can draw here is the SOP expression can be converted into the POS by adding the inverter logic gates at the end of the AND OR logic. So kalau you tengok the previous slide, so this is the AND OR logic. Okay, we have ABX is equal to AB plus CD, right? And then by adding the inverter at the end of the OR gates, we'll get the POS expression. Alright, so far ada soalan? Ada?
No.
No question, Alright, okay, next we have the XOR logic gate. Okay, XOR logic gate is a circuit which will give you the output of 1, okay, whenever ataupun bila salah satu inputs dia adalah 1, okay. Whenever the inputs A or B is high, you will get the output of 1 or high, okay. If both inputs are high, the output will be 0, okay. If both inputs are high or low, the output will be 0. Okay, either A or B is 1, so you will get the output is 1. And how can we write the logic gates for exclusive OR? So first you write the AB. So first first AND gate will be A is equal to 1. So by adding the inverter here, so you get the A is equal to 0. Okay, here is gate number 2 and here is gate number 1. Then for the the B1 is B is 1 and this is B is 0. All right, and then to combine the expression of these two AND gate, so you will have B bar plus A bar B. Okay, so remember to only write the expression when the output is 1, okay, because this is the SOP, the sum of product. And how to write the XOR symbol by we call this the encircle plus sign. Okay, bila ada plus berada dalam bulatan ni, this is the encircle, ENCIRCLED, encircle plus sign. Okay, and alright, so you also can see we can write either A bar B plus A B bar or A bar B plus A bar B. So dia punya sequence dia tak ada it's same either you want to write this gate first or the second gate later and inversely. And this is the logic circuit for XOR. Let's see exclusive NOR logic. Okay, kalau kat sini we have the output of the XOR logic is equal to AB bar plus A bar B. Next, for exclusive NOR, by adding the inverter at the end of the XOR, we will get the XNOR. So from the expression, this is the previous XOR gate, just add the inverter. Inverter is equal to the vertical line, alright? So just add the vertical line on top of the XOR expression, you will get the expression for exclusive NOR gates, okay? And it's opposite with the XOR gate. So if either A or B is high, the output will be low, alright? And if both AB is are high or low, the output will be high. So dia adalah opposite to the XOR logic. And for the Boolean expression for XNOR logic, we will have A encircle plus sign B with the vertical bar on top of the expression. And how to rewrite or simplify this expression is using the De Morgan theorem. Break the bar, change the sign. So we will have, so kita break the bar yang atas ni, kita akan dapat A B bar, okay, and then A bar B with the big bar on top, vertical bar on top of this. Alright, so double bar is equal to we can cancel the double bar, so apa yang tinggal ialah A bar plus B. So again we will implement the De Morgan theorem. Okay, kita break the bar, kita akan tukar sign from multiplication to the addition here. So A bar B plus B multiple A sini dapat A kerana kita ada double bar here. If there are the double bar, we can cancel. And A plus B bar. And you can expand or simplify this A bar B plus B times by A plus B bar is equal to A bar B bar plus AB. Okay, yang ni you have to refer the 12 Boolean rules in order to get the A bar B plus AB. And then from this expression, sometimes you are required to write or to draw the logic circuit from this expression. So from here we can see that ini adalah first term A bar B bar ialah first AND gate. Sorry. Okay, and then the second one is AB with plus sign. Plus sign is always referred to the AND gate. Okay, so you will have AB plus A bar B bar and AB. So here A, you need to add the inverter because sini A dia akan jadi A bar here, and then from input B, you add the inverter or the invert logic, you will get the B bar. So A bar, B bar will be the first input terms for this OR gate, and then the second input will be the AB. Okay, AB, you just connect the wire from the very before the inverter gate. So this is a first term from the first AND gate, and then this is the second term from the second gate, and the combinational logic for this X NOR will be X is equal to A bar B bar plus AB. Any question? No? Alright, let's proceed to the next slide. Implementing combinational logic. So how or where we can implement, or when we can implement the combinational logic circuit. Okay, so it's I think we have discussed this before. We can design or we can draw the logic circuit from the Boolean expression. And then, for example, let's see here, for every Boolean expression, there is a logic circuit, and for every logic circuit, there is a Boolean expression. It means that we can draw the logic circuit from this expression. Okay, so let's see the first example. X is equal to AB plus CDE, and then you can see here this AB is the this X is the combination, or the we can compose it from the AB plus CDE with 5 variables. I'll try to draw. Okay, sebentar. Sorry. Nampak tak saya punya slide sekarang?
Nampak.
Nampak.
Alright, so kita tengok yang ni. So the first example is it said that the X is composed from the AB. This is a first AND gate, and gate number 1. This is AND gate number 2. Okay, so normally we will start draw from the second term. Okay, kalau for this three, for this AND gate number 2, it got C, D, and E with 3 inputs. Okay, and then the first gate will have the A and B, and then to combine, the combination is combine. You want to combine multiple gates to get one input. Okay, so to combine these two terms, we need the OR gate. So this will be X. So X will be AB plus CDE. Okay, so when the question asks you to draw the logic circuit from the Boolean expression, so this is how you draw the gates. Okay, and then the second one, you have the X is equal to AB times CD bar plus EF. So let's see the oops. I'll share the screen again. Alright, so okay, let's see another example. X is equal to AB multiplied by CD bar plus EF, where AB, CD, and EF, we have 3 terms here. Terms 1, terms 2, and terms 3 are they are composed from AND gates. Okay, so kita akan ada 3 AND gates with 2 and then we can this CD and EF will be combined by the OR gates. Okay, and what's the benefit to make this to combine in this combinational logic? We will have less overall of propagation delay. Yang ni bila you dah start connect circuit, nanti you akan nampak effect dia. Contoh bila kita simplify from this expression to this expression, so it's also equal to, if you expand the expression, you will get the ABCD bar plus ABEF. So daripada expression ni, you can generate 2 types of logic circuit. Okay, let's see. Alright, so this is for the first one, and this is for the second one. Okay, the simplified version, the B one. Okay, okay, from A tadi kita ada AB times CD bar plus EF. So we will have like AB, CD bar, and EF, the AND gate for this one. So like I mentioned earlier, we start with the last term. Okay, so kita akan ada EF. Okay, EF is the combination of input E and F in AND gate, and then we have a CD input, CD bar, so you have another AND gate, and then at the D input you need to add the inverter because we want to have the D bar. Okay, so to combine CD bar and EF, you need to have the OR gates. Okay, so this is the SOP for the first term. Okay, the combination of CD bar and EF, you combine using this OR gate, so you will get CD bar plus EF. Okay, next, this combination you need to connect to the another AND gate. Okay, AND gate with AB inputs. So at the end, you will get the X is equal to AB plus AB multiplied with the CD bar plus EF. So this is the output from the first term. Okay, this is first term, this is second term. So you will have the X is equal to AB times by CD bar plus EF. Okay, any question so far? Okay, there. Alright, so in order to simplify from A, in order to write the ABCD bar plus ABEF, okay, kita tengok yang ni expression yang kedua. So you have ABCD bar plus ABEF. So this is first AND gate and this is second AND gate. So you will have 4 inputs for each of the gates. Okay. Alright, so the first AND gate will be selalu kita kena tengok yang paling belakang dulu. So you will have the AB and EF. Input A, B and EF for the second gate, and then for the first gate you will have the AB, C and D bar. So for the D bar you need to add the inverter at the after the D input. So you will get this. To combine these two AND gates, you need to have the OR gate. So X is equal to ABCD bar plus AB, E and F. So the X now will be the SOP implementation from the circuit in figure A. Any question? Hari ni berapa bulan? 18 hari bulan. Nur Atirah Muhammad Daud, are you there?
Yes.
Okay, boleh faham how we convert from A to B?
Boleh, madam.
Yeah, simple
Yeah.
Alright. Zulhilmi, are you still there?
Yes, madam.
Okay, boleh faham? How can we get A from B from A?
Yes.
Yes, Alright. So this is the normal ataupun soalan-soalan yang biasa ditanyalah dalam exam. Okay, kalau tadi kita design the logic circuit from the Boolean expression. Now we want to design or draw the logic circuit from the truth table. So if you begin with a truth table of an expression, you can write the SOP expression from the truth table and then implement or draw the logic circuit. And you always need to remember that the SOP, the sum of product, is the AND OR implementation, and for the POS is AND OR invert, okay, gates, AOI implementation. POS is AOI, SOP is AND OR implementation. Alright, let's see the first example. How can we draw the logic circuit from the truth table? Yang ni pun kita dah basically kita dah discuss in the previous session. Okay, the Boolean SOP expression obtained from the truth table by ORing. ORing is OR is the sum. We sum the product from this two outputs. Okay, so this is A bar, B and C is the first term of the SOP, and then the second term of SOP we have the A, B bar and C bar. Okay, kalau kita tengok A, B and C, kita ada berapa variables? Ainul, Hafiz, Berapa variable dalam truth table ni?
3.
3. So input dia akan ada A, B and C. So for the first gate, we have A bar. So for the input A, we need to add the inverter after the A to get the A bar, and then for the B is the normal B, and then C also without the inverter. So this is the first term of A, B, C bar. Okay, the second gate we have the A ialah daripada first A ni, A without the bar, and then B bar, B, and then we invert to get the B bar for the second input. For the third input, we have the C bar. So the output for the second gate will be the product term of A, B bar and C bar. So to combine these two SOP, we use the OR gate. So X is equal to A bar B C plus A B bar C bar. Okay. Next, let's see the next example. Design the logic circuit based on the truth table. Truth table given. Okay, so step number 1. Let's say only the output is equal to 1. Okay, tengok pada output sama dengan 1 sahaja when the output is high. Okay, so we have 3 terms here. So it means that in your logic circuit, you will have 3 AND gates. Okay, so the first AND gates will be composed by A bar, B and C. So this is A bar, B and C. The second one is A, B bar and C, and then the third one is A, B and C bars. So, and it will be sum ataupun it will be combined by using the OR gate. Okay, and remember to add inverter in each of the A, B and C to get the bar. Alright. I think this is simple, okay, from truth table to the logic circuit. But normally in the question, dia tak akan tanya sesenang inilah. Let's see next another related example. Okay, this is from the you need to simplify the logic circuit given. Alright. So you are given this logic circuit and then you need to simplify to this small one. Okay, daripada 1, 2, 3, 4 AND gates with 1 OR gate, you need to simplify to 2 AND gates with 1 OR gate. Okay, first what you need to do is to write the XOP expression from this logic gate. So let's see, for the first term, we have A, B bar and C bar. I think I will share the, saya nak conteng-conteng sikit. Alright, okay, so let's see the first term. Okay, this is a term 1, this is term 2, term 3 and term 4. Okay, and then it is from each of this gate. Okay, G1, gate 1, gate 2, gate 3 and gate 4. Okay. So we have A, B bar and C bar for this first gate, okay, first term plus A, B, C bar and D bar. For term number 2, number 3 we have A bar, B bar, C bar with D for term number 3. And then term number 4 we have input A bar, B bar, C bar and D bar. So to combine all these gate, we use the OR gates. Okay, the output from each term will be the combination of will be combined using the OR gate. So the X will be this term. Okay, and from the expression you need to draw the K-map. Okay. Okay, sebab kita nak simplify the logic circuit. Okay, daripada this A to this B. Okay. So in order to simplify the expression, we have discussed this in the previous lecture using the K-map. So the first one is kita ada berapa? 1, 2, 3 dan 4. Okay. So first A bar ini adalah ABC ialah non standard expression, right? So you need to convert to the standard standard expression of SOP first in order for you to draw the K-map. Okay, I will not share or I will not discuss the previous how can we convert from non-standard to standard, but you can refer to the previous lecture. Alright, so from the SOP expression, this is SOP expression. X is blah 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 blah, and then in order to simplify the circuit, you need to use the K-map and always remember to write only one. Okay, before you draw the K-map, you need to draw the step before the K-map. Siapa ingat? Syafiq Hakimi?
Ya,
Yeah, what is the step before we draw the K-map?
Sudah lupa.
Sudah lupa? You need to draw the truth table.
Truth table.
Okay, sebab you nak tahu yang mana yang you nak mapkan one dalam table ni kan, dalam map ni. So you kena ada truth table. Before that you need to have the truth table. Okay, bila you dah buat truth table, you akan dapat satu dari expression ni, barulah you boleh circle the expression. Okay, Syafiq boleh?
Okay, thank you, madam.
Okay, so please refer the previous lecture notes. I already uploaded to the ULearn tool. How can we get the K-map from the truth table? So all these steps from write the expression to the draw the K-map, semua ada markah ya, and biasanya kalau macam ni dia tak assist you pun. First you kena you kena draw the truth table and then K-map, and then baru you dapat the simplified version of logic circuit. So you need to remember the step before you simplify the version of Boolean expression. First kita kena ada the standard form of SOP expression. Kalau you tengok kat sini, A, B, C, yang ni missing term is D. So you kena dapatkan D punya the first term with variables D. So that's why here you will get 1, 2, 3, 4, 5. So this 5 ones is coming from truth table. Okay. So bila you dah dapat this one from the truth table, you can circle ataupun loop D1. Okay. So let's see the first loop. Okay. How to circle the loop. First to find the most yang satu yang paling banyak, and then remember dia punya loop ialah kena ada sama ada 2, 4 atau 8. Semua adalah to the power of n. Okay, kita tak boleh ada loop satu je bulatan tu, tak boleh. Sekurang-kurangnya 2. And then we start with the biggest numbers of 1. Okay, kalau here we have 1, 1, 1, 1, and then we loop by combining this row and the last row. Alright, so the how to simplify expression from the K-map. The first loop we have 4 ones, and then how to write the expression from the loop macam I cakap last time. So first you tengok AB. Okay, this AB yang mana adalah sama. So A kita ada A ialah 0 dan 1. So 0 dan 1 tak sama, so kita tak boleh ambil dia. So kita akan only consider the same variable, which is B bar. Okay, so write B bar here. And then the second one you have a CD. CD ialah 00 dengan 01. C ialah 0, so here is C ialah 0, and D ialah 0 and 1. So we only consider the same variable, which is the C bar. So the answer or the expression or the output from the first loop will be B bar and C bar. And then for the second loop, okay, here kita ada 2. So how can we write the expression from these two okay, these loops? So kita tengok dia ada A, B and CD. CD 0, 0. So C bar and B bar. And then for the A, B only A ialah sama. B kita tak dapat yang sama. So we will have the final answer will be A, C, B bar. Okay, from the final expression, we can draw the final output for the logic circuit. With the first gate is with the 3 input of A, C bar and D bar, and then the second gate will be B bar and C bar. And to implement the combinational logic, you use the OR gate, okay, to combine these two terms, right? Any question? Star, car, sun, Laos?
No, madam.
No, faham eh?
Faham.
Okay, so you need to refer the previous lecture notes again. How can we make the non-standard form to standard form expression? Okay, we came to the third part of the chapter where we would like to have the NAND and NOR gate as the universal logic gates. Okay, kenapa kita panggil universal? NAND and NOR are known as universal gate because all logic gates can be represented by NAND or NOR. Okay, later we will see how each of the logic gates, for example, the AND gate, the OR gate can be the combination from the NAND or NOR gates. Okay, and NAND and NOR gates also are the cheapest and smallest gates to manufacture in IC compared to the AND gate. Therefore, none and nor are almost always used in the practical circuit design. And De Morgan's theorem is most commonly used to transform all logic gates to NAND gates or NOR gate. So remember theorem number 1 and theorem number 2, if you break the bar, you need to change the operator. So for theorem number 1, so x plus y and then bar, if you break the bar, break the vertical line on the top, you need to change from plus to the multiplication. So you will have x bar times by y bar, and theorem number 2, you will have from x multiplied by y bar is equal to x bar plus y bar. Break the bar, change the operator. Okay, so let's see how NAND gate can be converted to the simple logic gates. Okay, for this combinational NAND logic gate, you need to remember ataupun you kena ingat bagaimana this inverter is coming from the one NAND gate. Okay, so for example, here we have input A, so this is NAND gate, so NAND gate A will be A bar. So it is same if you have the inverter gates. So satu NAND gate sama dengan inverter, okay? And then if you have two NAND gate, it is same as the AND gate. So input A and B. So this is NAND gate number 1. So you will have AB bar, okay? And then again you add the second NAND gate, you will have AB double bar. So double bar will be cancelled, is equal to AB. So it's also equal to AND gate. So 2 NAND gate is equal to AND gate. Okay, yang ni kena ingat Number 3, the OR gate are can be the combination from the 3 OR gate. So let's see how can we design the OR gate from the NAND gates. Okay, gate number 1, NAND gate number 1. So we have A here. So this is A bar. B here we have B bar. So A bar, B bar, NAND gate. A bar, B bar, NAND gate is means that you need to add the vertical line is equal to A plus B. So A plus B is equal to the OR gate. Okay, number 4, if you have a 4 gate, so this is the first 3 is equal to the previous OR gate. Okay, kat sini ialah OR gate. Kita tambah lagi satu NAND gate. We have the output will be A plus B bar. So it is equal to NOR gate, not OR. Okay. So A, B, kita tambah inverter kat depan, kita akan jadi NOR gate. Any question so far? Siti Hajar, are you still there? Hello, hello. Trisvita Kau.
Yes, ma'am.
Okay, ada soalan?
No.
No, faham How can we get the basic gates from the combination of NAND gate? Alright. Okay. This is for the NAND gate, and let's see how can we use the NOR gate as a universal logic element. Okay. Again, same as the NAND gate, kita boleh design the inverter from the NOR gate. So we have NOR, we know that NOR is what? The multiplication, right? So A is equal to A bar sama dengan inverter. If you have input A, if you invert it will be A bar. So the second one, you will have the two NOR gate as an OR gate. Okay, so input A and input B. In the NOR gate, you will have A, B bar. So A, B bar, again, you as an input go through the NOR gate, you will cancel the bar, so you will have the AB. So 2 NOR gate is equal to 1 OR gate. Okay. Number 3 NOR gate will be same as AND gate, and if we add another NOR gate at the output of 3 NOR gate, you will get the NAND gate. So let's you can try how this 3 NOR gate convert to NAND gate using 4 NOR gates. Okay. And for the next, okay, what is the mixed logic? Okay, and biasanya mixed logic ni kita adalah the combination from either only NAND gates or only NOR gates. Okay, it depends to the question. And why we need this mixed logic? It's allow a digital logic circuit designer to implement the combinational logic with either of these two. Okay, and yang biasanya akan I'm not sure, but we normally use NAND gate. Maybe sebab dia senang kan, dia darab instead of tambah in NOR gates. Okay. See, alright. So how can we combine the logic circuit using only NAND gates? So from the De Morgan's theorem, we know that the NAND gate can function as a negative OR. Okay. So this is NAND A, B bar is equal to, break the bar, change the operation. So A bar, from multiplication, you will have the addition, A bar plus B bar. Okay, so this A bar plus B bar, we can we can write as a negative OR gate. Okay, negative OR lah sebab A dia adalah bar kat sini, B pun ialah bar, and then we combine A and B with the OR gates. Okay. Logic diagram using NAND gate should be drawn using NAND, okay, or negative OR. Negative OR also known as dual symbol diagrams. And by using the dual symbol diagram, it makes it easier to determine the output expression directly from the diagram. Okay, kalau kita guna negative OR, lagi senang untuk kita combine the terms or the to combine the terms and then to get the output expression. Sebab kita guna OR adalah simbol tambah, ya. Alright, let's see the example of this mixed logic. I think we miss the input here. Let's see. Kalau kat sini akan ada ni garis B ni akan ada garis ini satu, A and D also. Okay, you can refer to the notes in PDF in the ULearn. Okay, for the first so for the original version. Okay, so the step to solve this kind of question is either implements all or in the Boolean function, and okay, first you need to implement all or in the Boolean function The second one, you need to implement all ends in the Boolean function. And the third one, first you need to forget all the inversion at this moment. So kalau kita tengok di output, okay, this is a function f a b c d, so is equal to b c plus a d n. We have a bar. Okay, first kita akan lukis, draw the b c and a d, and then without dengan forget all the inversion at this moment. So you will have, this is first first BC and the second one is AD. Okay, BC and AD, and then will be combined by the OR gate here. Okay, this will be X. Okay, the second step. Okay, draw the vertical bars in the circuit where all the complement in the Boolean occur. So tadi kita dah lukis B, C, and we have the bar. Okay, so B, C bar, you akan lukis the vertical bars in the circuit. Okay, lukis vertical bar here, and then for D, we have D bar here. Okay, just write the vertical bar first, and then the combination of B, C bar and AD bar also got the bar. Okay, add the bar at the output, and then last one, draw a bubble on each of vertical bar. Okay, lepas you lukis ataupun draw the vertical lines, you add the bubble in front of the vertical bar. So it's mean the inversion ataupun kita dah invert from kita dah invert the complement of each of the variable. So this is the the logic circuit from this expression. So but remember, this B got line, B also got line, A also got line here. And then the question from this expression, assume this design use NAND gates only. Okay, daripada this expression, you need to draw using the NAND gates only. This is a very famous question given the combinational logic circuit, but you need to redraw the circuit using only NAND gates or only NOR gates. Okay. Alright, so you need to convert each gate to the desired gate. Okay, kalau question asks you to design only use NAND gate, so you need to design ataupun convert each gate ni kepada NAND gates only. Alright, so the previous gate we have this AND gate, and OR gates. Alright, so by adding the bubble, okay, alright, so if only NAND gate is available, insert a bubble in front of the AND gate. So untuk convert from AND to NAND gate, you need to add the bubble in front of the NAND gate. Okay, okay. So for the first two gates, you add the bubble here. Satu untuk gate number 1, and then for gate number 2, add bubble in front of the output here. And then we also know that the NAND gate here is equal to XOR gate. Tadi kita tengok yang ni, negative OR gate. Okay, this NAND gate is equal to negative OR gate. So that's why you add insert a bubble, adding two bubble on the input side of the OR gate. So this is the input side of OR gate. So it's also equal to this NAND gate. Okay, yang bubble and vertical lines ni adalah daripada previous steps. Alright, so what is next? Alright, so you need to balance the bubble on each wire. Okay, so kalau ada odd number of bubbles, for example, here odd numbers, you need to add an inverter or another bubbles. Okay, so kalau kat sini tadi dia dah ada kan, so tak perlulah, tak perlu tambah. Ini adalah satu, you kena tambah inverter kat sini. And then you need to, if there is an odd number of bubble on wire, add an inverter. Yang inilah odd, you kena tambah inverter. And remove this vertical bars bubble. Okay, you need to remove this vertical bar. Okay. Alright. And next step is, okay, we know that the inverter is equal to NAND gate. Okay, this is okay. Kalau kat sini you ada bubble, you can cancel the bubble. Okay, kalau ada dua bubble boleh cancel. Alright, kat sini pun nanti you boleh cancel. Alright, so this will be one AND gate. This is a big one AND gate. The inverter will be converted to the NAND gate. Sorry, not AND gate, but it's NAND gate. So inverter will be first NAND gate, second NAND gate, third NAND gate. Yang tadi ada inverter kat sini, kita tukar jadi NAND gate juga. So this is XNOR is equal to NAND gate, and the last inverter also will be NAND gate. So altogether we have 1, 2, 3, 4, 5, 6 NAND gate. Right, so from this expression, BC bar plus AD bar can be composed using 6 NAND gate. Okay, so daripada first version, okay, daripada first version kita ada yang ni kan, 1, 2 NAND gate, 1 OR gate with 3 inverter can be converted into the final version of 6 NAND gates. Okay, so you need to play around how can you convert from AND or an inverter to only NAND gates. Okay, nanti you boleh try and play around. Let's see, either Gan Kai Fen is still here.
Yes, madam.
Do you understand what I explained here just now?
Yes.
Yes, eh?
Yes.
Okay, good. Alright, let's see next slide. Kita ada 63 slide, but the rest are the example how can we convert from the logic gates to NAND gates or NOR gates. So kalau I tak sempat nak cover semua, you boleh try by your own revision. Okay, we know that the inverters can be implemented by either a NAND or a NOR gates. Okay, and then the input will be wired together. So kalau inverter, it will be either NAND gate or NOR gates. Alright. Okay, let's see another example of how can we convert these logic gates, but only use the NAND gate. Okay, put the SOP expression using NAND gates only, and this expression can be implemented. First, this expression can be implemented using 2 NAND gates and 1 OR gate. So at the very beginning, you need to draw this expression using the normal gates. Okay, so for the normal gates, like I mentioned earlier, you need to start with E. E adalah satu input je. So the CD is the second gate, second AND gate and AB is the first AND gate. Okay, and to combine those 1, 2, 3, 4, 5 variables, we need to have the OR gate to get the final expression F is equal to AB plus CD plus E. Okay, but the question needs you to put the SOP expression using NAND gates only. Okay, in order to put the SOP expression, you need to convert this logic circuit using the AND gates only. NAND gates only. All right, and then rewrite the expression using the De Morgan's theorem. Okay, sebab kita tahu by using De Morgan's theorem, we can convert to the NAND gates. Okay, so by adding the bar, okay, on the top of the expression, double bar is equal to 1, so it will not change the final expression. So you will get the AB bar times, okay, yang ni plus akan convert to multiplication, CD multiplied by E. Okay, so each terms got what? Separate bar. Okay, and then with double bar across the A, B, C, D, and E. So this is how De Morgan's theorem changed from AB plus CD plus E to the AB bar, CD bar, E bar, and then we have the bar on top of all the expression. So AB bar is the first NAND gate, CD bar second NAND gate, and C with E bar can be combined with these two NAND gates using the third NAND gate. So the final expression, or the F, is equal to, by using the NAND gate, you will get the AB bar times by CD bar times E bar, and we have bar on top of all the expression. Here, the final bar is equal to the inverter, the last bubble before we have F. Okay, so another example using NAND gates, but now we want to implement the XOR gate. Okay, the ataupun negative OR gate. Add bubbles with transformation circuit NAND to negative OR. Okay, negative OR yang tadi, the previous slide, the previous expression, logic circuit, dan the third gate here ni, the NAND gate can be converted to the NOR negative OR. Okay, the negative OR with 3 input. So for each of the input, you need to add the you need to add the apa kita kata, bubble kat depan tu. So here you will have the AB plus CD plus E. Kenapa E? Sebab kita dah cancel bubble here. Bubble kita akan cancel. Sini pun cancel. Sini pun cancel. Alright. So instead of AB bar, now we have AB plus CD plus E, and then with double bar. Alright. Inverted comma ni is also equal to bar. Okay, like I told you before, bar also can be write as the inverted, ataupun we call it as negate. B negate A negate is equal to A bar B bar. Alright. Okay, so inverted input OR gate is equal to NAND gate. So like we kita discuss sebelum ni. So yang previous here, okay, yang ni adalah sama dengan yang ni. Right, this is from previous slide, and we also, kalau soalan tu ask you to write in the negative OR, gate, so you need to use this negative OR gate instead of the NAND gate. Okay. Okay, another example using the NAND gate. I will go through another one example before we go to the NOR gate. Okay, so next example is we have the output X is equal to A plus B C bar. Okay, plus B bar C D and then bar on top of the CD. Okay, first step is just draw the normal combinational logic circuit before we convert to the final NAND gate. Kalau kita tengok kat sini, kita akan ada 1, 2, 3. Okay, BCD and gate, BC and gate, and then will be combined with the A, and then lastly we use the OR gate to combine 1, 2, 3 expression. Okay, so B, C and D bar. Okay, B and C. Let's see the version in this slide. Alright, it's easier to draw on. Alright, here. Okay, first kita akan ada this color thickness. Okay, this is from B. You boleh start mana-mana Kalau I biasa start yang daripada last kali. So we have B, C and D bar. But in the question it didn't mention we can use 3 input or 3 output. But normally if NAND gates, kalau dia cakap NAND gate, you only need you always need to refer to this NAND gate with 2 inputs. Okay, so we have B bar and C here as one NAND gate, and then B, C, D bar as second NAND gates. Okay, B bar, C bar, gate number 1, and then will be combined with D. Okay, sini kita akan ada B bar and C, and then because we need to have bar on top of this, that's why we add not here. So that's why here we got the B, C and bar, input D here. Okay, so second NAND gate, second gate of G2 here, and then we have a BC. Okay, ini adalah gate number 3 with input B and C, and it will be sum with the A. Okay, A ialah gate number 4. Okay, combined with OR gate because of the plus. Okay, so this B, C plus A. Okay, sini kita akan dapat A plus B, C. This A plus B, C will be invert. So add the inverter here. So you will have A plus B, C, invert, and then to combine you need another gate number 5 here. Okay, G5 OR gate. So the output X will be A plus B, C bar plus B bar C, D, B bar C bar and D. So this will be X. Alright, and then this is first step that you need to write the expression from the original. You need to draw the logic circuit from the original expression. Okay, step number 2. Okay, let's use another color. Okay. Okay, ini step number 2. Okay, we know that this NAND gate, NAND gate is equal to this X negative OR gate, jadi sama. So we have the first OR gate, if we have the OR gate, you can convert to the this negative OR. Yang ni you kena refer to the here. Okay. Alright, so let's see. Go back to this. So this OR gate, I think there's a notes you need to see. Okay. I will paste this note into the chat box for your information. This. Alright, so AND gate. Okay, convert each gate to the desired. If none, okay, or to none. Okay, how to convert from OR gate to NAND gate? By adding 2 bubbles on the input side of OR. Okay, you need to use this De Morgan theorems to convert this. Okay, this here. Okay, to convert OR to NAND. Okay, sini kita ada OR kan, kita nak NAND gate, so you need to add 2 bubble on the input side of OR. So that's why here we add 2 bubbles. Okay, ada bubble number 1, bubble number 2. Okay, yang lagi kat mana lagi kita ada OR gate, sini OR gate 1, sini OR gate 2. Okay, this also need to be convert into need to add the 2 bubble here. Okay, and then yang lain-lain kita akan this bubble kena transfer to here, and alright, so this AND gate will be convert into the NAND gate. Okay, that's why we have the third step here where this this OR gate now will be the NAND gate number 1. Okay, this will be NAND gate number 2, and kat sini kita convert, this is already NAND gate sebab bubble ni kita kena what we call, kalau ada bubble kat sini tadi, you need to kita kena samakan dia. Okay, daripada sini terus pergi ke sini. Okay, that's why we have the third NAND gate here. Again, same as here. This is B, fourth NAND gate, and then this is fifth NAND gate. Okay, so all together, and then we have the OR inverter here. 1, 2, sekarang kita ada 5, and then at the very last, because we have 1 inverter here, 2 inverter here, this inverter is equal to NAND gate. Okay, this originally is coming from this 1, and then this also B, B inverter 2. Okay, and then where else we have the inverter? I think no more. So altogether we will have 7 NAND gates. Okay, 1, 2, 3, 4, 5, and then 2 inverter 1 and 2. So altogether we will have 7 NAND gates. From number 1, from 3 NAND gates and 2 OR gate, we will have 7 NAND gates. All right. Ada soalan? Let's see. Go. Chi Seng, you have any question? Is Go still here? Tak ada soalan ataupun tak faham? Tak ada Okay, you can try by your own self after this. Alright, let's see. Next slide. How can I go back? Yes, here. Share option. Alright. You guys masih bersama saya ke? Ataupun dah ke laut dalam? I hope you are still Okay. Brace yourself for another 30 minutes. Okay. Alright, let's see. I will not go through this example because it's still in NAND gates. You can try by yourself. And let's see. Okay, how about build the prior circuit with only NOR gate? Kalau tadi kita consider only NAND gate, so now how about the only NOR gates? Okay. From the De Morgan theorem, we know that the NOR gate can be functioned as negative N. Kalau tadi NAND gate can be functioned as negative OR. So now opposite to the negative OR, we have the negative N. Okay. Logic diagram using NOR gate should be drawn using NOR or negative N, which dual symbol diagram. Make it easier to determine the output expression directly from the diagram. Okay, kalau same example, but you only need to use NOR gate. Okay, again, you have to add the vertical line at B, A, and D. Okay, so first, like I mentioned earlier, you need to write the logic gate for original gates here. So we have BC for NAND gate number 1 and AD for AND gate number 2, and then will be combined using the OR gate. Okay, so at the very beginning you don't need to add the vertical line. Okay, first. Okay, next. Alright, so for the next step, you add the vertical bar for each of the inversion. Okay, now barulah you add the vertical bar. Okay, vertical bar ni yang panjang ni lah. Okay. Okay, BC, because we have BC bar, so add the vertical bar at the output of BC, and then we have the D bar. So D bar need to add the vertical bar after the input D. Okay, and then the F output will be OR bar. Okay, selepas OR gate ni, you need to add the OR bar, and then you need to add the bubble next to each of the vertical bar. Okay, setiap kali ada vertical bar, add the bubble. Sebab itu bermaksud kita invert. And alright, so now we assume this design use NOR gates only. Okay, kalau tadi kita kita convert to NAND gates only. Now we convert this design to NOR gates only. So remember, this NOR gate is equal to negative N. Okay, so convert each gate to NOR gate. Bagaimana? So by adding the two bubbles here, okay, is equal to NOR gate. Okay, XN gate is equal to NOR gate. Okay, so we will have 1, 2 NOR gate. Kat sini dah ada NOR. Alright, so assume balanced number of bubble on each wire. Kalau tadi kat sini tak ada yang mana yang tak ada bubble, kalau ia ada single bubble saja, you need to add the another inverter. Alright, and we know that single bubble is equal to the inverter, so inverter also equal to NOR gate. Alright, okay, so you at the end you will get 1, 2, 3, 4, 5, 6, 7 NOR gate by balance number of bubble on which wire and substitute all gates to NOR. Okay, kalau NOR gate the inverter is equal to 1 NOR gate. Okay, so you have 1, 2, 3, 4, 5, 6, 7 NOR gate to be used to convert from this, okay, daripada 2 AND gate and 1 OR gate with 3 inverter, you will have 7 NOR gates to be used. Okay. Next, let's see another example of how can we implement the NOR gates. Okay, first, by ignoring all the inversion, ignore all the bar, ignore all the inverter, you just draw the logic gates. Okay. Okay, first we'll start with B plus C D. Okay, this is C. Kalau I tengok contoh ni, dia start with B. Where's B? Okay, this is B plus CD. C. Let's see the bigger version. Alright, here. Okay, so F is equal to A bar plus B plus C plus A bar B plus C D bar. Okay, yang ni pun ada bar, and then lastly we have the bar here. So kalau saya akan tengok yang paling belakang, kita tengok C and D first. Okay, C and D as gate number 1. Okay, this is C and D. It will be at gate number 2 is OR gate. Okay, add with input B. Okay, input B. So here you will have B plus C D. Okay, next this B plus CD will be combined with A inputs. Okay, this is A. So you get here A multiply by B plus CD. Yang ni you just ignore all the inverter. Okay, and then next this output, okay, will be this is gate number 3. Okay, 3, and this is gate number 4. You have to add the C. Okay, C here, gate number 4. Okay, or gate number 4, and then the final one. Okay, we have 1, 2, 3 input kat sini. Okay, we have B and A bar. Okay, here we have C plus A, B plus C and D. Okay, ini adalah to A, and this will be B. Okay, and this will be F, the output F. So again, I advise you to start with the very last expression in order to write or to draw the logic circuit. Okay, and then you need to add the vertical bar for each of the inversion. Okay, tadi kita dah buat yang without the bar. Now we need to add the bar or bubble, the vertical bar and bubble for each of the inversion. So first we have the D bar here. So D plus the inverter here. And then we have A bar. This is A bar. Okay, daripada A kita letak bar. And then next we have the C. Okay, not C ya. A bar lagi kat sini. Alright, this is next A bar, which is here. And then the output of this will be also invert. Okay, yang ni ada inverter here, so you need to add vertical bar. And then this also the next double bar. I tulis B2, so this is output from B2. And then lastly you have the B3. Okay, B3 bar number 3 is here. Okay, so this is B1. So this is B1 is the output. Okay, so you already add the vertical or bar, vertical bubble for each inversion. Alright, so assume this design use NAND gates only. So same as okay, ini adalah example untuk NAND gates juga. Alright, so kita ada mana tadi? Alright, so this bubble need to be convert as the inverter. Sebab kita tahu bubble sama dengan one inverter is equal to one NAND gate. Okay, inverter is equal to one NAND gate. Sorry ini adalah example for NAND gates juga. So I think it doesn't matter NOR gate or NAND gate. So you can try the example. Okay. So you will add one sini ya. Okay. Daripada sini kita akan jadi balance the bubble for each wire with the inverter. Okay. Mana-mana yang ada bubble, you need to add the inverter, okay, to balance the bubbles. Alright, so add the bubbles. Kalau yang tak ada bubble kat sini tadi, kalau ada single, add the inverter, okay. And double bubble will be cancel. Okay, kat sini dia ada 1, 2, dia akan tinggal 1 lastly. Alright, and we also know that this is equal to negative or is equal to NAND gate. Okay, and that's why we have NAND gate here. And all the inverter will be converted to the NAND gates. Replace all the gates to the NAND gate. You will get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 NAND gates altogether. Okay, and then one of them is a triple input NAND gate. Okay, yang last kali ialah triple input NAND gates. Okay, ini another example that you need to convert into the NOR gates. Okay, you can try by yourself. Ini another example using the NAND gates. Sama juga. Another example using NAND gates. I think sampai ke yes, yeah. We have until slide number 63 altogether, and the rest from page 50 tadi, sorry, from page 40 until 60, semua tu adalah example how can you convert the combinational logic to either none only or nor only gates. Okay, ada soalan atau tidak? I think yeah, that's all from me for this session. Ada soalan?
Tak ada rasanya.
Tak ada Faham tak? It's quite difficult to communicate using this, but I think you need to get used again with this kind of session. Semua dah ada, semua masih ada yang belum bergerak lagi kan? Ada yang masih di rumah, right?
betul.
Yes.
Yang masih di rumah boleh start kemas barang lah. Bila last datang campus 20 ya?
21.
21. Oh, I thought it's 20. Ada yang dari PKPD tak yang tak boleh datang? Dari Kedah ada tak?
Ada.
Lepas tu you stay kat rumah lah sampai habis.
I think so.
Syok lah Saya pun Kedah juga kampung tapi tak boleh balik. Well, you stay safe dekat Kedah tu. I think Kedah the numbers of positive patient now increasing
Betul.
Oh kat Alostar ke? Atau kat mana?
Lostak.
Alostar Saya Sungai Petani. Alright, okay, kalau tak ada soalan, I think that's all from me. We'll see again bila? Next week. Next week, from the teaching plan, we will have the lab session, but I'm still try to figure out how our lab session will be conduct. Virtually. I'm not sure yet. I will discuss with Dr. Faiz for our session, and make sure you proceed with your online discussion with your teammates regarding the assignment. Okay? Boleh?
Boleh.
And then the deadline for the assignment still on the 1st June 1 hari bulan 6. Tak ada extension because you need to work online with your teammates. Alright, kalau tak ada soalan, I think that's all from me. Let me see tadi siapa? Aiman Hakim dengan siapa yang saya tak tanda? Aiman Hakim je lah.
Dengan saya pun, Khairul Zamil.
Siapa? Khairul Zamil. Berapa nombor awak dalam ni? Saya tak nampak lah.
Nombor
8. Nombor 8, group
S2K1.
Group 1. Kita mata. Alright, ada. Yes.
Yes, lagi boleh.
Siapa nama? Nombor berapa? Boleh beritahu saya?
Lagi tak ingat apa.
Group berapa? Group 1.
Group 2.
Group 2. Badul Munir, betul?
Yeah.
Alright. Boleh bagi tahu tak siapa saya tu? I can't read your name from the chat. Aiman Hakim. Yes, Aiman Hakim. Aiman Hakim, group berapa? Aiman Hakim dah keluar dah.
Aiman Hakim S2K2.
S2K2, nombor, nama, alamak, I tak nampak lah. Aiman Hakim. Aiman Hakim. I can't see your name, Aiman. Okey, tak apa. Yang boleh tulis nama siapa yang tak sempat tanda attendance tadi, nanti I check balik. Nurul Nasahuda S2K1. Alright, tak apa, nanti I tulis Alright, thank you very much for all for the time, and I'll see you again next week. Stay safe, and siapa yang on the way balik tu jaga SOP, and kita jumpa next week. Alright, Assalamualaikum warahmatullahi wabarakatuh, and have a nice day. Bye bye.
Thank you, madam.
Thank you, madam.
Bye.
Thank you, madam.
Madam.
See you.
Okay.
Salam.
Thank
Thank
you.
you.
Madam.
Okay, bye.
Take one. Thank you, madam.
Alright, thank you. See ya. Okay, now saya nak ambil attendance dulu. You can just leave.